Conic sections by Eliza, Drew Stewart, and Maya Grenice.
Okay, so how we started our project was brainstorming how we wanted to create our models, and we quickly came up with the idea of using paper to create a visual plane that essentially cuts through the cone to outline the shapes of a circle, ellipse, a hyperbola, and a parabola. This was all done in the collaboratory. The hyperbola and parabola concepts were trickier to get our heads around, but after some thought and modeling, we were able to model them. We were one of the first, if not the first groups, to create this style model to show each shape as well. This is the explanation of our process. So first, we traced a circle on a piece of paper, cut it out, and fitted the paper onto the cone. Then we traced an ellipse from an image off of Desmos, and to make a perfect ellipse, and cut out an ellipse shape from the paper and fitted it onto the cone, but this time at an angle. And then we took two cones and cut holes through the tip with scissors. Once we inserted a wooden stick through the middle to fit them together, we glued the two cones together to further sturdy it, make it stand up by itself. Once we had the cones together, we traced a parabola on both of the cones, the same distance away from the center, the same size, almost exactly, and the same relative position. Then we cut along the outline of the hyperbola and fit a piece of paper onto the cones. We then glued the pieces from the paper cones onto the paper to create the illusion of a plane bisecting the cones with the rest of the cones still attached. The image should be helpful in aiding my explanation because that might be confusing. And we did the same thing with the parabola, but with a single cone for that one because there's only one parabola.
These are our final models for the circle and the ellipse. And these are the models for the hyperbola and the parabola. Now for the images and shapes in Desmos, we first looked at the circle. This one was pretty straightforward. Once we had the image of the circle and the circle centered into Desmos, we looked at the vertices to determine the radius. Once we found the radius by zooming in on Desmos, which was 3, we squared it, which made the equation equal to 9. And then we added the other side of the equation, which was x squared and y squared, because the vertex is the origin. Therefore, the h and k values are 0. And that's how we got our final equation.
Moving on to the ellipse. Once we put it into Desmos with the center on 0, 0, we looked at our vertices and co-vertices. The vertices of the x-axis were 1.414, 0, looking at the ending of the white section and starting at the black paper. To find the a value in our equation, we squared the number to get our a value of 2. To find the b value, we looked at the y value for the co-vertice. We observed this value as approximately 1.225. Looking at where the white ends and the black starts on the image, and then squared this to be 1.5 for our b value.
Now for the hyperbola, and this one caused much confusion. Once we had the image of our hyperbola inserted into Desmos, we did not know how to determine the sort of slope, the width of the openings on the hyperbola. I'm not sure how to the term, and we guessed and checked the b squared until the equation fit our pieces of cone, a paper cone. And then the points on the hyperbola that were closest to origin were 0, 2 and 0, -2. So we knew that the a squared value underneath the x squared value in our equation is 4 because 2 squared equals 4. With the b squared value being 0.5, we figured out that the b value is 0.7. And then we created the lines on Desmos as followed: y equals 2, y equals -2, and x equals 0.7 and -0.7. This created our rectangle for the hyperbola. The intersecting corners gave us our asymptotes. I'll explain how we did this. We clicked on the point of all the corners and found the difference in x value and y value, which gave us our slope. The top left corner and the bottom right corner were 4 spaces apart on the y-axis and 1.4 spaces on the x-axis, and for slope, rise over run, that came out to be 4 over 1.4x, and that was the same for the other 4 corners, except for the negative and positive sign. And that's our hyperbola.
For the parabola, we estimated that the vertex is 0, 2.64 by zooming in on Desmos. We know that the equation for an upside-down parabola will be in the form of x minus h squared equals 4p y minus k. So we plugged in 2.64 for our k value. Therefore, our equation so far is x squared equals 4p times y minus 2.64. To find the p value of our equation, we needed a point on the parabola. We used an x-intercept of negative 2.050. We plugged the x and y values into our equation to get a p-value of 0.4. We then multiplied 0.4 by 4 to get our final equation of x squared equals negative 1.6 times 4 minus 2.66. The 1.6 is negative because the parabola is facing down. This is our work for finding the circle and the ellipse, and our work for finding the hyperbola and parabola.
When searching for our conic sections in real life, we discovered that they could be found in the most common places. First, we were driving by McDonald's and realized the sign contained 2 parabolas. The logo contains 2 arcs with vertices, making it 2 parabolas. Secondly, we went to Chipotle and discovered their burrito bowls are given in ellipse-shaped containers. The container features 2 vertices on either side of the ellipse, with arcs connecting them, creating the ellipse shape. Thirdly, while at Chipotle, we discovered that their seating was circular chairs, so the perfect place to take a photo. The seats were round, with the outside being equidistant from the center. Finally, we returned home with frustrated faces, frantically searching for a hyperbola around my house. Then we looked at my parents' collection of blue glasses and saw that one contained a hyperbola since the sides caved in to create 2 vertices and created 2 arcs on the sides that were opposite of each other. Looking at all of those examples, it is clear that the conic sections play a large role in the design of our world. For example, logos, household items, and even restaurant furniture and items are all part of conic sections. These conic sections make up the world around us.
Thanks for watching. Those were our conic sections.